putting it back. I would have loved to grab things off the shelf as I was running to catch my flight yesterday, and I would probably buy more than I did because I had to stop. So that's a completely different retail experience that is created. But the second thing, imagine what kind of information Amazon can collect in addition to what you buy. They can collect what you almost bought. What you put back. Did you put it back because you didn't like it? What was your face like? What were your emotions? Did you put it back because you didn't like it? Or did you put it back because you liked something else? How long did you hold it? All this information, this new kind of information is there to be collected, and you can bet yourself that Amazon will not just collect this information and use it, it will sell it. So that's an exponential thinking of how you create completely new business models and new opportunities using AI, not just efficiency gains. Second example that I like to talk about are driverless cars. Maybe my favorite example. Driverless cars, again, a technology that's entirely driven by AI. We've been talking about driverless cars for a century, but suddenly they're happening. We'll talk about why they're happening now. Again, how is that going to affect your business? A lot of people think, okay, I'm not in the transportation business. Driverless cars are cool. Maybe I'm going to commute using a driverless car, but it's not really going to affect my business. But driverless cars, again, are not just by efficiency gains, about efficiency gains. They're not just about replacing your drivers or reducing the cost of your transportation. They're going to create an entirely new economy. And we'll talk more about that. That's the nonlinear effect of technology, and specifically AI, which has driven these two examples. So I can give you a lot of examples of how things are moving forward and where things are going, but I want to give you a little bit of an idea of sort of what is driving this. What is happening now that is making this move forward? And there's really a couple of different factors that are driving this. I'm going to move this out of the way here. I know it's important, but it's exactly where I want to stand. All right. So there's a couple of different things that are happening. And Jordy showed you the Moore's Law, and maybe that's the first reason that things are moving forward, because after all, AI is a software. Software is moving forward at an exponential rate because it is riding Moore's Law. Now, here's the thing. When you look at Moore's Law like this is a log scale where every tick here is 100-fold faster than the tick before it. This is called a log chart. And it takes this exponential curve and squishes it into something that looks almost like a line. And that tends to be deceptive, because you look at this and you logically understand it's an exponential, but your brain tells you, oh, this is just a straight line. So I took this data and I plotted it on the linear scale, so you can see really how fast computers are going to have been over the past century. Right? So I'm going to show you this chart. This is the real data. This is not an illustration. This is not an artist's depiction. This is not conceptual. This is the real data of how fast computers have been in gigaflops. How many gigaflops you can buy for $1, right? Over the past century. Look where we are today. This is how fast things are moving forward. You look at this, it's almost amazing that we could do anything in the year 2000, right? Year 2000, 2010 looks like a joke compared to today. This is how fast things are moving forward. Now, in case you're getting too excited as if we're sort of finally hit the upwards trend, let me show you what this chart is going to look like 10 years from today. So let's assume Moore's Law keeps on going for 10 years. It's been going on for 120 years. So let's assume it's going to keep on for 10 years. This is what it's going to look like. This is 2028, but this is where we are today on that chart. 10 years from today, you will look backwards at 2018. This is what's going to be on this chart. This is not an illustration. This is real data. What does it mean to your business? What does it mean to your children? What does it mean to you, to your career, when things are moving this fast when it comes to computers? And a lot of people will say, okay, this is cool, but there's no way this can keep on going on. A lot of experts will keep on saying this has to stop. But it doesn't. It keeps on going. In fact, Google recently came out with this TPU, 180 teraflops that you can use. The students use this. and this is this red dot over there at the top right. So this curve is peeling upward. So this chart that I showed you how fast computers are going, it is going to keep going up. So this is the first reason why AI is moving forward so fast. It is because obviously it's riding Moore's law. Now, it's tempting to think that AI rides this curve, therefore it's moving so fast, and that's it, that's the end of the story. But there are other factors that are driving AI. So I want to tell you a little bit more about what is happening around AI. One of them is the way we think about artificial intelligence has changed over the past couple of decades. The way we build AI systems has changed. And to give you an idea of how that has changed, I'll give you sort of a 60 seconds primer on how AI works. And the truth is that there's really two ways to build an AI system traditionally. One is using rules, where a clever software developer writes down rules, if then else. In this situation do this, in that situation do that. And the computer just executes these rules very, very quickly. That's a traditional way of building AI systems. You can build a system that plays chess and checkers and go using lots of rules and so on. The second approach for building an AI system is one that is based on probabilities. Where you don't give the computer rules, you just give it lots of examples, and the computer calculates the odds of certain things happening. You remember from high school this mathematical puzzle where there's a bag full of marbles, and what are the chances that you're going to pull out a blue marble if you pulled out a red marble before, and so on. These are probabilities. The computer just looks at this and calculates the odds based on data, just statistically, just probability. So these are the two approaches of building AI systems, and in fact, from the early days of AI, from the 90s, 50s, both of these approaches of building AI systems already were in existence. 1957, IBM demonstrates an algorithm that plays and beats the world champion in checkers, 1957, on live TV, using rules. A logical algorithm that can play checkers, and it beats the world champion. 1957, a year later, Frank Rosenblatt creates this AI system that has a camera, a digital camera, before Kodak, 400 pixels, 20 by 20, and a neural network with 8 neurons. And it can look at an object and automatically tell if it's a triangle, a square, or a circle. Automatically, not because somebody wrote down rules. A triangle has 3 corners, a square has 4 corners. No, just because it has seen these objects before. An amazing technology. We call this machine learning. The New York Times goes wild that the world is going to end. Machines can learn. But then the AI community comes back and says, this is interesting, but it's impractical. Where are you going to get data? How are you going to store data? How are you going to transmit data? How fast can computers learn? It's too slow. It's interesting. But for the next 50 years, the AI community believes that rules are always better than data. Even though you can build AI systems with both approaches, rules are always better. And I like to compare rules to sort of logic-based intelligence, reasoning-based intelligence, and data-driven machine learning to intuition-based intelligence. Intelligence that's based on experience. And the AI world has battled these two approaches. There's always almost a dichotomy in how people thought about AI. Some people believed in rules, some people believed in data. For the first 50 years, rules won. But that equation began to change as data is becoming abundant. So the second exponential that is driving AI today is the exponential growth in data. Because today AI is this explosive combination of data and algorithms, machine learning algorithms. And we liken data to the fuel and machine learning algorithms to the engine. They're both useless on their own, but when you put them together, you take off, and this is what is happening today. Because you have to remember that rules-based AI is very efficient and fast, but it does not get better with time. It is not clear how to make a rule-based system improve. You have to add rules. You need an expert to write down and code the rules. But A machine learning system is easy to improve. You just give it more and more data. This is what is happening now. It's taking off in a big way. And there's lots of charts about exponential growth of data. Jody showed you one. Here's my favorite. This is the number of cameras sold until 2014. And you can see what an exponential graph actually looks like. 2014. 2015, nobody's measuring. 2016, 17. There's just, every phone has 5 cameras. Every car has 10 cameras. Every building has 10,000 cameras. Nobody's measuring it. These cameras are themselves getting faster, cheaper, and better, higher resolution, higher frame rate. And this in itself is just fuel. Now these are just cameras, but there's also motion sensors and GPS sensors and thousands of sensors out there. We'll talk more about sensors later on. All these sensors are generating fuel. And it's not just physical sensors like that. It's even a camera that can measure how many people are passing by an advertisement on the street. That's a sensor. It's a data stream. All these data streams are producing fuel for AI that is getting better and better. But it turns out that there are some types of challenges that even the best AI software and the best machine learning methods could not solve up until just a few years ago. In fact, up until 6 years ago, not even the best company with the best AI and the best and the fastest computers can do certain things. Up until 6 years ago, no AI company or software could reliably tell the difference between a cat and a dog, for example. Isn't that embarrassing? Even a 1-year-old can tell the difference between a cat and a dog, but no AI software could tell the difference between a cat and a dog reliably up until 6 years ago. With all the machine learning and all of Moore's law and all of these different ideas, nothing seemed to work. Now you can say, who cares about cats and dogs? But what about bicycles and motorcycles? You cannot drive down a busy city intersection if you can't tell the difference between these two things. And yet no software could tell the difference reliably between these two objects. The situation was so bad that in 2010 the AI community released 1 million images in an attempt to crowdsource the solution. So the AI community said, here's 1 million images broken down into 1,000 different categories, 1,000 images of sunflower, 1,000 images of Superman, 1,000 images of sushi, 1,000 images of 1,000 different categories, 1 million images in total. They said, here's this data set, download it, and let's see if anybody can write software that will automatically recognize what's in the software, what's in the image. 2010. Now, there's a big competition, and everybody competed. And by the way, humans can get it right 95% of the time. So the question is, how well can software do it? So there's a big competition, 2010, everybody competed, big companies, small companies, hackers, universities, anybody and everybody in the AI business was writing software that can understand what's in an image. The day of the competition came, September 30, 2010, and the best software came in. The best software got it right 75% of the time. So, I didn't know about you, but I don't want to be sleeping in the back of a driverless car that gets it right 75% of the time. 75% of the time is good enough for winning the world championship in chess. 75% of the time is good enough for winning the stock market, but not for driving a car. So interestingly, we've always thought that playing chess is an intelligent thing, but actually telling the difference between a cat and a dog is a lot harder than playing chess. It's just that we are so good at it, we don't even understand how difficult that is. 2011 comes along, the competition is run again. Everybody competes, big companies, small companies, universities, hackers all over the world. Everybody who is in the AI business is writing software. And the day of the competition comes along. September 30, the best software comes out, and its performance is 75%. The needle is not moving on this problem for almost 30 years. Nobody seems to be able to write software that can understand what it is seeing. almost trivial thing. 2012 comes along, competition is run again. September 30 comes along, the best software is still 25% error, 75% success. But September 30, midnight comes along, and suddenly the error drops down to almost 16%. Drops down by half. I remember that day. I remember my students bursting into my office telling me somebody brought down the error on machine vision, on machine perception. It was software that was called supervision. Now it is called deep learning, which you may have heard of this term, deep learning. The new, if you need to remember one name in machine learning, one technology, it is deep learning. Came out in 2012 by University of Toronto, and not only did they release the software, they also released it open source so that everybody could copy it. The next year, everybody copies it. Error goes down to 10%. And remember, humans can get it like 5% of the time. So we're still okay, still safe. Next year, the error goes down to almost 5%. 2015, the error goes down to 3.5%. 2016, it goes down to 2.9%. Machines are twice as good as the average person in understanding what they're seeing. 2017, the competition is no longer held. It is too easy for computers to understand what they're seeing. Embarrassingly, behind the scenes, it's this guy's algorithm from 1957, except that Frank Rosenblatt had 400 pixels in his camera and 8 neurons in one layer. Today's networks, deep networks, are the same structure more or less, but they have not 400 pixels, they have 4K pixels, not one layer, but many layers, not 8 neurons, but millions of neurons. But the interesting thing about this is that the more neurons you add, the better the machine gets, the better the machine learning algorithm gets. This is very different than the rule-based AI system. Remember, rule-based AI, we did not know how to improve. It is not obvious how to add rules to make a rule-based AI system better. But if you want to make a neural network, a machine learning system better, you just add neurons. In fact, half of the papers that are coming out now in AI are basically adding more layers and making layers bigger and wider and longer. So now a machine can look at an image like this and tell you in a nanosecond, here's a dog, a child, a chair, and here's another chair. In a nanosecond. This is just the beginning, because this image has red and green pixels over here. It was made for human consumption, but a computer doesn't need to see the world in red, green, and blue. A computer can see the world in the whole swath of the spectrum. A computer can see the world at night, in the dark, high frame rate. A computer can see the world not with 2 eyes, but with 20 eyes. So this is just the beginning of how a machine can see the world. And it's only going to get better. This is part, again, of that exponential deceptive curve. This is just the beginning of how machines, it's not about beating humans, it's only going to get better from here on out. So when you look at a driverless car and you're wondering, why are driverless cars taking off today? After all, we could drive cars from a computer a long time ago. Cars had millions of lines of code and thousands of microprocessors decades ago. So why are driverless cars taking off today? What has happened? And what has happened is just one small thing, that up until 5 years ago, cars couldn't tell the difference between a pothole and an oil spill, between a toddler and a fire hydrant. Up until 5 years ago, computers could not tell the difference between these two things, so they could not drive across a city street. But now they can, and this is the last piece of the puzzle that allows driverless cars to happen. So now computers can understand what they're seeing, not because some clever software developer wrote a special algorithm. Maybe it's going to be another pesticide company because it's going to come out with another pesticide, a better chemical. But it's going to be AI that's going to disrupt the pesticide business. This is how AI worms its way into every business. And this is what I want you to go back home with. This is what it looks like through the neural network. You have robots that can work side by side next to people for the first time because they can see the people. And they can learn from the people. Now, importantly, all this technology is open source. Anybody can download this. In fact, Google, Amazon, Facebook, Microsoft, Baidu, they're all pushing this software out for free. Tencent is even giving the computing power for free. Google is giving computing power for free. But what is not free? The data. Computing power is free, the machine learning algorithms, but data is not free. Data is the asset. And I bet that you are sitting on data. We'll talk more about data later on. The data that you are sitting on, the unique data sets and the business opportunities that these data sets are useful for, that's your asset. Because the AI is free and the computing power is free. But there's also a dark side to this, and that is that we don't know what the machine is actually learning. I want to give you one example of a real story that happened to us. We were building a robot that was supposed to stand on stage in front of a large audience at NIPS, the biggest conference in AI. It was supposed to stand in front of 2,000 AI experts, and we were going to do this demo, where we were going to show up in front of the robot and wave a banana or a water bottle, and the robot would yell out, "Banana, water bottle," just like you're waving a water bottle right there. So that was the demo supposed to be, and it sounds silly, but that was state of the art just a few years ago. So it was such high stakes that we were preparing this demo for weeks in the lab. My students were, waving all kinds of things in front of the robot and training it and making sure it could recognize this object. And then something really strange happened. What you're seeing here is a snapshot from the screens of one of the software developers, and you're seeing in the top left is the live view of what the robot is seeing. And the right half side grid shows you what about 200 neurons in this large neural network are responding to. So you can see that in this live view, some of the neurons, like this neuron here, is not responding to anything. It's dark, and this one is dark. But some neurons, in particular the one over there, seems to be responding to something. So this is like sticking 200 electrodes into a brain and seeing how it's responding to something. If you stuck 200 electrodes into my brain, you would also see that most neurons are not responding to anything, and so it's dark. But that neuron over there seemed to be very, very active, so we zoomed in to see what it was doing. And it turns out that that particular neuron was tracking the developers. You see them moving around the lab, the two guys, and this neuron is tracking the face, and even the face of the guy in the back. So we were really puzzled because we only trained the system to track water bottles, to identify water bottles and bananas and apples, and a couple of things we were going to show at the conference, and yet it was tracking the developers. What was going on? Was this a prank, a hack? So we thought about this for a while, really puzzled, and then we think we know what happened, but we're not sure. We think that what happened is that the AI learned that it was always these people that brought the water bottle and the banana. And if it could track them, it could do a better job at identifying when the banana and the water bottle comes in front of the robot. So this was at once both amazing and terrifying. Amazing because the AI learned on its own, not just what it needed to do, but what it needed to learn in order to do what it needed to do. But it's also terrifying because who knows what else it is tracking, and this is just the beginning. This is something simple, we understand, we can point to. But what else can it track when they can see with 20 eyes in the dark with sensors that we don't have? All right, so the final exponential that is driving AI is the cloud. And I know that the cloud is something that you probably think you already understand. You already upload to the cloud and offload to the cloud, and you already use the cloud in lots of different ways. But the cloud means something very different when it comes to AI. What it means is AI teaching other AI. There's even no name for it yet. It's not machine learning, it's machine teaching. It's AIs teaching other AI systems. So for example, driverless cars. A human can have one lifetime of experience of driving, but driverless cars can have many lifetimes because they can teach each other. If one car has an experience, it can share that experience with all other cars. So in a strange way, the more driverless cars there are on the road, the better each one of them gets. This is not true for humans. We don't become better drivers because there are more drivers on the road. But cars do, and this is a self-amplifying effect, and whenever you hear a self-amplifying effect, you can bet you there is an exponential behind it. This app that can detect skin cancer gets better the more people use it. But your doctor does not get better the more doctors there are, but the app gets better the more apps there are.
Sure.
This is an exponential growth, and it gets even faster when you have two systems pitched against each other. For example, if you want an AI system that can learn how to play chess, you don't train it on data of games. You have it play against another AI system that plays chess. These two systems will play chess against each other 1 million games a second and amass a huge amount of experience in no time. In other words, they will generate their own data. And this thing takes off. So I mentioned AlphaGo Zero that beat the world champion in Go about a year ago. A few months ago, AlphaGo Zero beat the software that beat the world champion in Go 100-0, purely by playing against it. A few weeks ago, another software came around, AlphaZero, and beat the software that beat the world champion, and it beat all other softwares, all other games, including Go, chess, checkers, and everything else, including Atari games, all at the same time in 8 hours, because it learns from all other AI systems. So remember, AI can teach AI. Here's another example. These are portraits of people that do not exist. They're all fake images created by an AI that is generating portraits again opposite another AI system that is determining whether that is a real portrait or a fake portrait. These two AI systems generate and critique a zillion portraits a second until the AI is so good it can generate as many realistic portraits as you want. These bedrooms do not exist. They're all fake. And the AI that learns how to generate it working against another AI that learns to understand what a bedroom is. These plants don't exist. These horses don't exist. These couches are fake. These buses don't exist. These buildings do not exist. Now, what does that mean for creativity? What does it mean to be an architect? When you can dream up a new building, when an AI can just dream up buildings out of in thin air 1 million a second. So this is how fast things are moving forward. So to summarize, we have 4 compounding exponentials moving us forward. Yes, at the bottom, there is Moore's law. And I want you to understand how fast this is moving forward. This is today compared to 100 years of computing power. This is the real curve, not an illustration. This is the real data. And remember, it's going to continue moving even faster. But it would be a mistake to think that AI is moving forward just because computers are getting faster. That's just a small piece of the puzzle. In fact, Moore's law could continue for another 100 years. We still could not tell the difference between a cat and a dog if we were still doing AI based on rules. But we have AI based on machine learning, which is driven by the exponential growth in data. So that's the second exponential, is exponential growth in data. Then we have the exponential growth in the capacity of the machine learning systems themselves, because we can keep on adding neurons. As the computers get faster, we make bigger and bigger networks, and they can learn and become more and more intelligent. And actually, last night I was wondering, how big do these networks need to be before they're competitive to humans? Where are they on the list? Because usually people compare this technology to humans on the basis of computing power. So I decided to compare this on the basis of size of a network. So here is a couple of different animals and the size of their brain in terms of the number of millions of neurons that they have. Okay, mouses and cats and raccoons, dogs and cats. By the way, this settles the debate of the dog versus a cat, okay, in case you're wondering. Who's smarter? And here's one of the biggest neural networks in the past year or two. Okay, so it's somewhere between a mouse and a rat. Still a long way to go, but remember, this is exponential. And the one thing that baffles me is why dolphins are so much smarter than humans. We still have to figure that out, but this is just a number of neurons in the brain. And finally, there's the cloud. The cloud that allows machines to move forward. So I want to end with talking a little bit about the future. So Jody talked about how these exponentials, when you zoom in, they're really lots of small waves, and every wave brings up another kind of technology. So I want to zoom in and try to understand what are the waves that are driving AI, because AI, when you zoom in, isn't really moving smoothly forward. It's moving in these small, in these waves. So I'm going to talk about 6 waves of AI that I can see. So the first wave that took about 50 years was the wave of rule-based AI. And that's the deceptive wave. That's the 50 years when AI was more of a hopeful term than a reality. And we do a lot of things with rules that are very useful, but it can only go so far. The second wave of AI is the wave of predictive analytics that happened in the 90s, and it's still going on. These are the first generation of machine learning algorithms that can predict the next row in a spreadsheet or the next column. And we use them to do things like predicting the stock market or predicting how many cucumbers we're going to sell next month. And you still have to do predictive analytics to stay in business, but it's not the future of AI. The third wave of AI is a wave of cognitive computing. It's the newfound ability of AI to understand not just numbers in a spreadsheet, but to understand things like images, video, audio, text, things that were impossible to understand just 6 years ago. So now computers can understand what they're seeing, and not just what they're seeing, they can read emotions from people's faces better than the average person, and not just people, they can even understand emotions of animals and so, whatever you want, as long as you can train the system. This is changing farming. It is enabling completely new business models like Amazon Go that we discussed earlier, because machines can understand what they are seeing, a ripple effect throughout the economy. Now I want to emphasize some things are still not solved. And this third wave that we're in, computers can do certain things. They can tell the difference between a cat and a dog very accurately, but one thing that AI cannot do today, and we have no clue, is understanding what you mean when you talk. So computers can understand what words you're saying, but not what you're actually meaning. So we call these chatbots, and you've heard a lot of chatbots recently. Chatbots typically still use a sort of almost 1950s rule-based dialogue tree to make conversation, and that's why they're so clumsy. In fact, you may have recently heard just a few weeks ago, or maybe a week ago, Google released Google Duplex that holds conversations, and I want to show you, play one clip from that conversation. This is a conversation between a human and an AI system, and they're trying to book a hair salon. So listen to this for a second and try to figure out who's the human voice and who's the AI. Let's take a listen. Got the volume up, please? Do we have volume?
We have it.
Okay, so this is an amazing conversation that you will not hear, but it's a conversation where it's, do you think we can make it work? Okay. You know, we like to say that AI is moving exponentially, but AV is not moving. So it's still a challenge. So it's an amazing technology, but when you listen to it, you realize that what Google was able to do is to figure out how to dumb down the AI so it says and maybe and could you repeat that, and it pretends to not understand, and that makes the conversation very, very natural. But there's still a big challenge to try to get that to work. Okay, so, okay, never mind, we'll just move forward. Okay, so, okay, so what's the next wave of AI? So the fourth wave of AI is the wave of creativity. So a lot of people will say, okay, AI is great at analyzing data, but can AI actually generate new ideas? And we call this creativity, artificial creativity. And I can see this sort of bubbling in academia, not quite yet made it into mainstream, but we see creativity or creative machine as the next wave of AI. So I showed you an example of how AI can generate pictures and things out of thin air. AI can generate design antennas better than the best designer can. AI can generate things like chairs and make them physically. Even proteins. AI can design proteins. So what's again unique about this fourth wave is it's not about consuming data and deciding is it a cat or a dog, or should I turn left or should I turn right? It's about generating new things. And that wave of creativity has not hit industry yet, but I can see it bubbling and it's going to come soon and change the world. And it's not just about designing proteins and antennas, it's really about things like music and art. For example, here's a painting robot that I have at home, and it paints oil on canvas. So it started off with my wife and I were taking oil painting classes in the weekends. And we were studying this for about a couple of months. And then the instructor comes to me, and I was sure he's going to congratulate me on how well I paint. And he said, maybe you should stick to building robots. And so I went home and I built this robot that paints. In the beginning it painted like me, but now it's getting better. It's learning. It's really painting large oil on canvas paintings. It's not Picasso, but it is better than many people. In fact, it just came out with this painting that won an international competition. It painted a flower out of its own imagination. It painted this portrait. Recently, I didn't know I was going to paint when I come home tomorrow. So, of course, where is all this going? What is DARPA putting money into? Not AI that can learn how to paint, but AI that can generate the next generation of AI. Okay, the fifth wave is the wave of physical embodiment. Now, interestingly, AI today is very virtual. Now, occasionally you see videos of robots that can do these kinds of things, but the reality is actually that robots and physical embodiments of AI is not very good. This is a recent DARPA competition around physical robots. Each robot here is $1 million. And these robots are not very good. It's very, very difficult to build AI in the physical world. AI will be able to drive your car tomorrow, but when the car breaks down, it's going to be a human that has to crawl around and fix it. So when we think about jobs, it's actually high-paying intellectual jobs that are in the crosshairs of AI. The physical labor that is unstructured, like nurses and construction workers and plumbers and electricians, are very, very difficult for AI to replace. And it has to do with the fact that while software is moving forward exponentially, material science isn't moving that fast. Batteries and actuators in the physical world is still slow. The last wave that I'm going to end with, the last wave that I can see of AI is the wave of sentience. What is sentience? Sentience is the ability of a machine to to feel, to have emotions.
Sentience.
So a lot of people will say, okay, machines can create art, they can create music, they can detect emotions in people, they can fake emotions, but can they have emotions? Can a machine really feel? And I believe the answer is yes, it will happen. And it happens when the machine takes all that AI capability that we use to model the world, and we turn it inside, and the AI begins to model itself. And I'll show you one example. This is a robot that we have in our lab that learns how to move. But what is unique about this robot is that it is blind. It cannot see anything about the world. It can only sense itself. And it learns how to walk not by doing trial and error in the physical world, not by being programmed by a computer developer, not by doing machine learning in the physical world, but it does it by learning what it is, by creating a self-image. And you can see in the first day out of 4 days, it has no clue what it is. If it's a spider, a snake, a tree. 2 days into the process, it's beginning to realize that it has 4 legs, but doesn't quite know how they're connected. 4 days into the process, it pretty much figured out that it has 4 legs. We're sort of peeking into its imagination, and we can see how it thinks about itself. It then uses that self-image that it has created of itself to figure out how to walk, not in reality, but how to walk in its imagination. And then here it is, walking in reality for the first time. And again, it did not do trials of walking before this, nor was it programmed directly by a human. It created an image of itself. To test this, we removed the leg and we watched what happened. And you can see that the robot initially doesn't understand what had happened, but after about a day, its self-image also loses a leg. And here its leg became a bit short in its self-model, and here it is learning how to move forward without a leg. And I know it looks very sad, but we did put the leg back again, and the robot is happily retired. But you can see here that the robot is learning how to move without a leg because it's self-image updated. It's not about, there wasn't a sensor that said leg came off, switch to plan B. It's all about self-model. So this is the beginning of, I think, what we call sentience. And the big question is sort of the ethical issues here. Is this a good thing or a bad thing that AI is moving forward so fast? And there's lots of people worried about it. People are worried about, for example, drones that can chase people and assassinate. But for every bad example or bad use of AI, I can give you a dozen good ones. The same technology that is used to make killer drones can also be used to make agriculture healthier and more productive for everybody. The same technology that will create a loss of jobs in driverless cars will also save 23,000 lives a week. That's the number of people who die from human-driven cars today over the world per week. It's more than all of drugs and gun violence and terrorism combined. It's at our fingertips to save all these people every week because of technology. The same technology that can lead to mass surveillance and is getting a lot of people worried is also finding missing children and can put an end to human trafficking altogether. So for every negative angle, I can see 1,000 positive applications, and it's really up to us to choose where it's going. And instead of a mirror, I like to think of AI as an amplifier. An amplifier that amplifies ourselves, and we just have to make the right choice and make sure it amplifies the right kind of traits. Thank you.
Well, that's given us a bit to think about. So what we're going to do now is just give you 5 minutes of think time. So the purpose of this is